From the Library of Congress in Washington, D.C.
So I'm Jennifer Harpster. I'm a researcher. I'm a research and reference specialist for the Science, Technology, and Business Division here at the Library of Congress. I'd like to welcome you to today's program, a rare astronomical event, the transit of Venus. This program is the third in a series of programs in 2012 that is presented through a partnership between my division and NASA's Goddard Spaceflight Center. And I believe this is our 6th year partnering with NASA. Our speaker today, Sten Odenwald, is an astrophysicist at Goddard and senior scientist with ADNET Systems, Inc. He received his bachelor's degree in astronomy from UC Berkeley and his master's and doctoral degrees in astronomy from Harvard University. Sten remembers the moment when his sense of wonder for the stars began. He was 10 years old, and his father pointed to the 3 stars in the belt of Orion and said, "Look how bright the 3 wise men are tonight." As a result, astronomy books replaced his rock collection. He became a fan of the science fiction television series Outer Limits, and he built his first telescope. These days, Sten investigates star formation, galaxy evolution, and the nature of cosmic infrared background. And he is currently studying the historical impact on humans of space weather, such as solar storms. A vigorous promoter of science education, Sten is the director of Space Math, a program that develops K-12 math problems featuring discoveries from across NASA. He shares his love of astronomy with the world with his award-winning Astronomy Cafe and space weather websites, as well as appearing in National Geographic television specials and Discovery Channel's Naked Science show. And he's not naked, I have to say. Sten also takes time to lend a helping hand to librarians. For example, several years ago, he helped me with a page on the Northern Lights for our Everyday Mysteries website. In 2004, he spoke at the library about the transit of Venus and assisted the music division with their web-based performing arts encyclopedia entry for John Philip Sousa's Transit of Venus March. We are happy to have Dr. Odenwald back to the library to talk with us about this rarest of planetary alignments. The transit of Venus comes in pairs, 8 years apart, but separated by more than a century. This year, the transit will be visible in North America the evening of June 5th. The previous transit, of course, was in 2004. After this lecture, I hope all of you mark your calendars so you will not miss this rare astronomical event, because we will not see another transit of Venus in our lifetime. The next transit will take place in 2117 and 2125. And now please join me in welcoming Dr. Sten Odenwald back to the Library of Congress.
Well, thank you very much. It's nice to be back here 8 years later. I think most stars tend to have a shorter re-invitation period than 8 years, but I'm grateful for the 8-year period. That works well. And that it's cosmically inspired, that's kind of cool too. Well, it all starts with Galileo. We're going to get to the transit momentarily, but talk a little bit about the technology and how the transit idea was even discovered in the first place. As we know, Galileo invented the telescope and used it to basically study Jupiter and the planets and also the sun and sunspots and things like that. You can't imagine what 1609 must have been like. I mean, Galileo, sort of invents this new technology. The general public had no concept of being able to view things at a distance using a telescope to magnify images. And so they didn't really have any real understanding of how to use the technology. The original attempts were actually confusing. The first attempt was probably illegal in most countries, and the other one is definitely an inappropriate use of the telescope to view the Pope. So it was a confused period, but eventually they got things straightened out. And Galileo observed Venus, planet Venus, discovered that it had phases, looked at Jupiter, discovered that it had moons. So that sort of begins our telescopic study of Venus. And since then, NASA with its spacecraft has done even better, of course. We can send spacecraft there and take firsthand observations of what Venus looks like. We can also use radar to look at the surface of Venus, which you cannot see because of its very thick atmosphere. So we've learned a lot about Venus. I'm not quite sure why we have feedback going on here.
Jennifer's just gone to see if somebody can.
Oh, okay. All right. And the other partner in the transit of Venus is, of course, the sun. And many of us don't intentionally look at the sun. And those times that we do, it's usually because we have a total solar eclipse and we're lucky enough to be in a location where you can actually see that. And when you see the moon in front of the sun during a total eclipse, you then see the beautiful corona of the sun, which we now know has great connections with space weather, as we call it. Transit of Venus looks like this. This is the 2004 transit, observed telescopically from the ground. And that's largely what you're going to be seeing this June 5th at 6:03 p.m. When you yourself make the observation using safety glasses. I didn't have these glasses available right now because they're being shipped. And when I get them, I'll bring about 200 of them here to the library. They'll be in the Adams Building Science and Tech Reading Room, and you can pick up your own personal safe viewing glasses for the transit. Your next challenge is to find some place here on Capitol Hill where you have a clear view of the western sky at sunset, because the transit is going to happen about starting 2 hours before sunset. So it's going to be kind of midway down the western sky, and the transit will continue through sunset and end at midnight. But of course, you won't be seeing it after sunset. The cool thing is, though, we have a number of parties around the world who are going to be broadcasting the transit on the web. So, as soon as you're finished viewing it personally and getting those photons of light, you can then go online and see the whole thing, plus narration in 3 or 4 different languages. The transit happens because the planet Venus gets between the Earth and the Sun. It does that normally because the orbit of Venus is inside the orbit of the Earth. So technically, you should have many occurrences where that happens. But the problem is that the orbit of Venus is tilted relative to the Earth. So there are only 2 places in Earth's orbit where you're going to have the possibility for transits. And that's when, as you see in this picture, Venus is at that so-called node point. If that node point is between the Earth and the Sun, then you have the opportunity for seeing a transit of Venus. Okay? So that's something about the geometry. Here's a NASA satellite, actually a NOAA satellite view of the transit of 2004. You can see Venus scooting across the lower portion of the image. That was a nice thing about 2004, is we had a number of satellites viewing the sun as part of their research. So we got these interesting views of the transit in different wavelengths of light, from X-ray through the optical. And that's something that previous observers had never really had access to. Here's a close-up of the Venus, the sort of disk of Venus seen against the photosphere of the sun. When the transit happened back in 2004, the sun was just coming down from sunspot maximum. That means that there were a declining number of sunspots on the face of the sun, and the sun was on its way towards its minimum state, where there's not a whole lot of activity. So pictures that you see of the transit of 2004, you typically will see a face of the sun that looks kind of bland, like there's not much going on. This time, however, we are within a year of sunspot maximum. So this transit is going to be really quite exciting to watch, because you'll have this very sharp black disk of Venus against a very active photosphere with probably many, many sunspots, large and small. So it'll be kind of artistically very interesting event. The geometry is sort of this way, that basically, here's the 2004 transit as an example. As viewed from the Earth, the planet Venus moves from Roman numeral 1 to Roman numeral 4 along its transit path. And that takes typically about 5.5 to 6 hours. So once the transit starts and we start observing it at 6 o'clock here in Washington on the 5th, it'll take about 6 hours, so it'll complete roughly around midnight or a tad after. And that's why you will sometimes see the transit referred to as June 5th and 6th, because the ending of the transit happens like, 1 a.m. sort of in the morning of June the 6th, rather. Are we the first? I mean, how far back in time can we go and see people that have observed the transit? Probably there is some suggestion from archaeological evidence and inscriptions on tombs that around the time of Montezuma, when there was a transit in 1520, he may have been able to see it. Because all you have to do is look at the sun around sunset, when you have the atmosphere kind of blocking a lot of the bright light from the sun, and you will be able to see the disk of Venus at sunset. All right. Any other time, and you'll be blinded, But at sunset, if the transit happens at sunset, there's enough atmospheric extinction that you don't need safety glasses, and you could actually see it. In fact, Chinese astronomers routinely observed very large sunspots on the sun using just this method. They wait for, sunset or just after sunrise, and they'd look at the disk of the sun to see if there were blemishes. 1631, that was the first transit in sort of the modern post-Montezuma era, if you will. It was predicted by Kepler, but was not visible in Europe. All right, so, that's a shame. And in 1631, we didn't have a lot of scientific stations spread around the world and not very good communication techniques. So, once Kepler predicts something, it takes like months for the word to get to the other side of the world by that time the transit is over. 1639, interesting first transit that is pretty well documented. Jeremiah Horrocks in England, he was a minister, church minister. He was recalculating the previous astronomical tables and discovered that people had miscalculated the orbit of Venus by just a little bit. And when he did it correctly, he found that there should be a transit of Venus visible from England in 1639. And sure enough, he got out there and observed this darn thing with basically projecting the image of the sun onto a screen and then watching for the dot. Unfortunately, he had sort of things that he had to do in the church, and so he only got to watch the first hour or two of the transit, and then he had to go off to minister to his congregation. And by the time he came back, it was done. And the frustrating thing is that here's this guy who's made this prediction and gone out there and made this discovery, of this thing happening just like the prediction. And you would think that in the history of humanity, he would be given sole credit for this wonderful happenstance. Wow, it's really him that did this. It turns out, he did the observation, but then just because this other person was interested in the sun too and looking at sunspots, Mr. William Crabtree, 3 towns over, observed the thing at exactly the same time. He was not as well dressed. But it's like this frustrating thing, and we see this many times in science, that, here's this, great person that makes this discovery, and you think that he'd be credited with the whole 9 yards. But nope, there's somebody out there in a little neighborhood, so they have to share the credit, which is fine. Everybody likes to share. We're adults. Well, so anyway, the reason why transits were so interesting is that Johannes Kepler, he had constructed mathematically a very precise model for the solar system, where he knew what the distances between the planets were compared to the distance of the Earth from the sun. Using that as one unit, Mercury was 0.35 units away from the sun, Jupiter was about 0.69, Earth was 1.0, Mars was 1.6, Jupiter was 5.2, and so on. He knew those numbers very precisely. But until you know the distance between the Earth and the Sun in kilometers, you don't know how big the whole shebang is. So that was what people were really anxious to get a handle on. And until they could do that, all they could do is basically do a proportionate model of the solar system and really not know how big the whole thing was. And so it turned out that a Scottish astronomer, Gregory, and an English astronomer, Halley, sometime later on, Gregory came up with this idea that, well, hey, if we know the distance between the Earth and Venus in terms of the scale thing, it's about 0.3 in these units. If we wait for Venus to pass in front of the Sun and measure that whole process from two observers in different parts of the Earth, they can use basically this parallax method to figure out how far away Venus is from the Earth in miles. And about 50 years later, Halley essentially went with this idea, codified it, worked out the rigorous mathematics, and because he had a reputation, compliments of Halley's Comet, he was not named after Halley's Comet, it went the other way, of course. But, he had the international, acumen to really pull this off. Gregory, not so much. So it became known as Halley's method, even though it's the Halley-Gregory method. So anyway, here is the run of transits from 1639 to 2004. We've got basically 122 and a half years coming up here, and we've got 8 years and 105.5 years. Those three timescales have to do with the details of the orbit of the Earth and Venus and where the nodes are and all those particulars. The interesting thing about that 8-year period is that if you work out where Venus is every 580 days, you discover that you can draw a perfect pentagram within the orbit of the Earth. And so you're often going to see the transit of Venus linked to pentagrams and pentacles and satanic kind of things because, whoa, the numbers work out and it's a perfect shape in terms of timing. So anyway, moving on, the 1761 transit, here we start. Instead of observed by only a couple of people, this one was observed by 176 people. Okay, so we're starting to get popular here, including Mikhail Lomonosov, who was an astronomer in Moscow, who basically noticed something really interesting about Venus as it moved on and off the disk of the Sun. That in those moments, as it was making that transition, the whole backside of Venus, the other part of the black circle of Venus, lit up just a little bit in terms of like a little luminous arc. And he interpreted that to mean that Venus had an atmosphere. And that, in fact, is 100% correct. So we discovered that Venus has an atmosphere through the transit of 1761. Also, there was some considerable but muted public reaction to the transit, usually as the butt of jokes in fashionable French newspapers. But anyway, I won't tell you what the joke is here. I don't even understand it. And in fact, that's the interesting thing. Over the period of 200 or 300 years, humor changes. And it's like, why was this funny? What is the sight gag going on in here? I have no idea. Anyway, 1769, we have Captain Cook. By now, French, British, and even American astronomers were really keen on looking at transits in order to better determine what the distance between the Earth and Venus, and therefore the Earth and the Sun was. So here we have the Cook expedition to Tahiti to set up a scientific station as far away from Britain as he could get. Probably a political statement too at the time, I don't know. But the idea is that you get as far apart as you can so that as viewed from those two different places, the path of Venus across the Sun shifts by a measurable amount. And that shift that you see against the Sun is related geometrically to how far apart the observers are here. And then by just working out a simple proportion, you then work out what the distance to Venus is. It's a very clean thing. Surveyors use that technique on Earth all the time as part of their tricks of the trade. So anyway, here's Captain Cook, doing his voyage. Also at that time, we had many precise measurements made. Timekeeping was crucial amongst these observers in far-flung locations because the only thing that you could do is to time when Venus started and ended its transit in order to establish what that chord was on the sun. Okay, and so they had to somehow coordinate timekeeping in one location on the Earth with timekeeping in another place. And in 1769, that was big science and engineering. That was huge. You know, bringing a clock from one place to another and synchronizing them to within literally seconds of accuracy. Hard thing to do. The next transit, well, interesting, in 1857, there was an interesting article about when the next transit should happen, and somehow somebody mangled their interview with the astronomer. And the newspaper sort of placed a correction, New York Times placed a correction as to when the next one would happen. And that was sort of a definitive correction on the earlier error. 1874, December 8th, photography was just getting started. There were huge numbers of photographs that were taken of this transit. Congress allocated $75,000 for international expeditions hosted by and run by American astronomers to go out to these far-flung places and to make these measurements and to stand toe-to-toe with the British. Okay, to basically show that, yes, we Americans can do just as competent and accurate astronomy as anybody else, you know, because we were still proving ourselves at that point. Now, $75,000 back then is like, what, $2 trillion now? I don't know what the conversion is, but it's huge. You know, we're talking, you know, tens of millions of dollars, I would think, you know, in terms of the resources that were expended. And Congress sort of wrote this check out, and Benjamin Franklin sort of was highly, you know, supportive of this, and in fact, he promoted an astronomer into the British Journal of Science, sort of co-sponsored him to publish his work on the transit. Benjamin Franklin was really big on this transit, and he was very influential at this time. So scientists got $75,000, a couple of ships, all the, you know, limes they can eat on the voyage, and off they went. And so the 1874 transit, the transit at that time, they were able to collect all this information together and come up with a number of 91 million miles for the distance between the Earth and the Sun, which is really cool because the previous number was like 60 million miles, and the previous number before that was 15 million miles. So now we had a pretty definitive measurement of what that distance was, and so therefore, with Kepler's scale model, we can now multiply that number against all these others and figure out how many miles is it really to Jupiter. Of course, when it was announced that there would be a transit in 1882, this met up with some interesting discussion, not very pleasant. Proctor was an astronomer and a popularizer, and you know, he made the claim correctly that there would be a transit in 1882. This was not greeted very well. Let the astronomers gratify their perverted taste by having transits in their own houses, but let them understand that the government will not lend itself to open, shameless astronomical junketing. I mean, you guys had already gotten $75,000 from us, and now what? You want to get $100,000 this time? You know, what is this? How long is this going to keep going? How long are you going to keep inventing transits and coming to us for money? Well, this will be the last time. Anyway. But there were other sort of perspectives too from the 1882 transit. You know, the New York Times and people were op-editing about this with lavish praise that this is just such cool stuff. You know, the simple everyday person can sort of get out there and with smoked glass look at the transit and realize that there are a bunch of scientists elsewhere doing the same thing, and they're coming up with numbers that tell you how big the universe is, you know, and they were just sort of harmonizing and resonating on this whole cosmic, you know, connection here going on. It's really cool to see. And so, you know, 1882, everybody was out there with their smoked glass. 10% of the population went blind, of course, but this worked pretty well. There were also pictures taken. The pictures that had been taken for the 1874 transit really had the right idea, but the problem was that when they brought these plates back and started analyzing, they realized that they hadn't properly controlled for the actual orientation of the photograph at the time of the observation. So they couldn't measure where the horizontal plane was in these photos, for each photo that was taken. And that's huge. That's a huge problem, because then you don't know really what the orientation of the sun is, and you don't know exactly how the position of Venus on the sun in one time relates to another time. So what they did for 1882 is that they took even more photographic plates, these glass plates that they developed on site with chemicals. They scored the bottom of the plate with a tiny channel, and they filled it with a drop of mercury. And so when the plate was held perfectly level with the ground, the mercury would fill the entire channel and give you an actual line on the photograph. Simple technology. It took all of 10 seconds to score the plate and put the mercury. Of course, mercury poisoning was a problem, but we don't know the graduate students that died from that little thing there. Graduate students are sort of the unsung heroes of a lot of things. You never hear about them, for the most part. But, we are legion. Anyway, and of course, the newspapers loved the transit too, and so they took a lot of liberties. There's actually an inscription around the disk of the sun there about, feeling uncomfortable that so many people are now looking at me, from the Earth, and I'm feeling embarrassed, and all this. Again, humor doesn't translate too well. Transit of Venus March, 1883, the year after the transit. Sousa was commissioned to write a march for the passing of Henry. He was a physicist, much loved, worked in electromagnetism and magnets and generators and inductors and things like that. Well, he died, and so he was a Mason, and so Sousa was a Mason, and so he was asked to write a commission, a march for the ceremony, the burial of Henry. So he did, and it's the Transit of Venus March. Because at the time that Henry was buried, or at the time of this inauguration, there was an interesting conjunction going on in the sky that involved Venus. It would be in the daytime, so nobody would see it, but Sousa knew about it, and of course the astronomers that were Masons also knew about it. So it was kind of a cosmic thing. It was still Venus as a theme, but now, it was the march. And let me see if I can play this for you. An interesting story here. Myself and Susan Claremont and Laura Schissel were sort of looking through records of music for things that had to do with Venus, and we found this unplayed Transit of Venus March. It was the score written for instruments in 1882, not for modern instruments. So my mission gave Loris money, commissioned him to transcribe this into modern instruments, and so he played it with his band, which is well known in this area. And so since then, it's now become popular for schools to play the Transit of Venus March, and here's one that's actually quite amusing. This goes on for 6 hours. But it's cute. All right. So anyway, if you go to YouTube, yes, thank you very much. You too can play this yourself and have a great time with it. I just found it really amusing. And this wasn't the end of it either, because there were a number of other things that came out of that transit as well, music-wise, the gallop and all sorts of things. Not a huge repertoire. Nobody's going to put these into a book that's going to have more than maybe 20 pages, but it's kind of fun. I mean, this transit, 1882, really captured a lot of people's attention, if you want to see more about the holdings that Library of Congress has, you can visit this website, which is part of the Encyclopedia of Music, and you can see all the resources that were found as a result. Really kind of fun. Things never change. The prospect of a Democratic victory is extremely alarming to Republican politicians, and they become more desperate as prospects brighten. But it has had no more to do with the depression of business than with the last total eclipse of the sun or the next transit of Venus. So there, we get all things mixed together into one sort of interesting pot. And here's another one, Senator Plum. Yes, that's a real person. You might as well speculate about the next transit of Venus to guess whether Indian territory will sometime be divided and made two distinct territorial governments, so forth and so on. So, you know, people use it as a kind of an expression for at least a period of time. We don't do that anymore. That's a shame. Anyway, okay, so the astronomical unit went from about 5 million miles to about 92.7, thanks to the transits of Venus. Modern technology lets us do really clever things like bounce radar pulses off of planets and asteroids, which we know distances to in Kepler's model, and come up with an astronomical unit that's good to a half a mile, which is what NASA needs in order to navigate around the solar system. And that's really kind of a cool connection to NASA. William Harkness at the U.S. Naval Observatory came up with this sort of famous comment. There'll be no other transits of Venus till the 21st century of our era has dawned upon the Earth and the June flowers are blooming in 2004, and so forth. And, you know, that's all true, but nobody said anything about cicadas. When the transit of Venus did dawn again in 2004, we had cicadas. Brood 10 reared its head, and 2004 will always go down in our history locally as the year of the cicadas and the transit of Venus. You know. NASA did some webcasts of the 2004 transit. Over 50 million viewers viewed this thing. I was in Greece, in Athens at the observatory there, working with Isabel Hawkins, another astronomer, and we narrated you know, a number of hours of the transit, coming up with all sorts of interesting anecdotes and quips and things, and, you know, literally pulling it out of thin air, you know, for all this time on the air. It's like, you know, gosh, I can't think of anything funny to say about this thing anymore, you know. It also turned out that the European Southern Observatory, together with another organization in Europe, had the VT 2004 project. They had 2,763 participants and 1,000 school classes, and they combined their observations over this global study area to come up with an astronomical unit that was good to about 11,000 miles. This was 5 times higher accuracy than what Harkness and others did back in 1882. The adopted value is different from what the students came up with by only about the diameter of the Earth. So that's amazing. We're going to do this again for 2012, but instead of having 1,000 classes and 2,700 participants, we're probably going to have closer to about 1 million participants in several thousand different locations. So, you know, what else can you do with a transit? You can measure it or you can observe it, you know, so that splits the world into 2 parties, you know, and so we do the best we can. Here's the 2004 transit, seen by the NASA TRACE satellite. At least the end of it. We also have the Swedish solar telescope in the Canary Islands observing the last part of the transit, the disk of Venus, and so forth. And we have the GOES-12 satellite, NOAA's Earth Studies satellite, in the X-ray. You can see the disk of Venus passing across the bottom part. All those bright yellow areas are sunspots and active regions where we have flaring activity and intense magnetic fields. And this was a time when the sun was coming down from its maximum activity period. If we do this image again in 2012 in a month, that image is going to just be completely filled with these yellow-white areas of activity and flares, and, you know, you might even have trouble actually seeing Venus. Interesting, if you measure the brightness of the sun, the power that it generates in a square meter on the Earth, which we use for solar energy. Every time you have sunspots, you get dips in the light, and that really big dip comes from a rather large sunspot group. But if you look at the far right, you see this very, very tiny little line. Well, that's the transit of Venus. That's when Venus entered the disk of the sun and left. And you don't even see it compared to the noise of all these dark sunspots. But you can measure it, and that's a testament to our science and technology that we can measure the brightness of the sun and actually see the transit of Venus. It turns out that that very same technique is used by NASA's Kepler satellite to discover now well over 2,000 transiting planets around other stars. same kind of an idea. You have a planet that goes in front of the star. The light from the star dims a little bit, and you can measure just by knowing the diameter of the star and the diameter of the planet, or the brightness dip, what the diameter of the planet is. So that's why we're coming up with all these Jupiter-sized exoplanets and Earth-sized ones. We're using exactly this technique, which you can see with the transit of Venus. Here are some other pictures that came from 2004. Interesting pictures. There's also a beer that was commissioned. I have 3 bottles remaining of that brew. 8-year-old beer. I'm not too anxious to sample it, but I will give it a try and then have my stomach pumped, no doubt. The people in the jet basically didn't see anything happening at all, right? I mean, because they're seeing the horizon of the Earth and, you know, everything else down there, and they look up and they see blue sky. It's just our perspective puts the jet in the same area as Venus and the sun. Kind of funny. And of course, we're going to have the usual screaming multitudes with their glasses. For 2012, we have a little bit of a different transit. The transit happens on the upper or northern part of the disk of the sun in that time. And we still have the interest in the first 2 moments when Venus goes onto the disk and the last 2 when it goes off the disk of the sun. And the timing of those things gives you basically what the length of that chord is, which then allows you to compare that against the length of the chord measured by another observer. And then the distance between those 2 gives you the parallax, as they call it, which is then related to how far apart observers are on the Earth, and then you can figure out what the distance to Venus is pretty easily. Our particular details for us, it starts on June the 5th, a Tuesday, at 6:03 p.m. So everybody is in the middle of rush hour traffic. And it ends at sunset. So we get to see the first 2 hours of the transit when Venus goes from not being on the sun to then being firmly on the sun. Okay. The transit ends a little bit after midnight, actually 1:30 or so a.m. That's why you will see the transit referred to as June 5th, 6th, because it overlaps the 2 days. Again, NASA is planning a lot of activities that are going to surround the transit of Venus. We've already developed a website over the last year with a lot of resources, historical and otherwise. Also, we're going to have a webcast from Hawaii, live webcast, which will be very exciting. Even more capably done than the first one 8 years ago, because we now know how to do it. Of course, we now don't have to do it again for another 120 years. So the learning curve then starts all over again the next time around, right? Because nobody's going to go back and look at how we did it this time. They're going to create something new. We have the webcast going on. That starts a little bit before 6 p.m. our time here in Washington. So if you go online to this website, you can connect up with the video stream for this, and that'll run through the entire transit into the early hours of the morning. We know that many museums are planning sleepover events for kids. Of course, it comes on June the 5th, which is sort of around the time many schools graduate by then. So it's a kind of a different event. The transit in 2004 was also like that as well. But we know from that experience that didn't prevent tens of thousands, hundreds of thousands of kids, streaming to local museums to have overnight, sleepovers to watch that event. And of course, we are on Facebook, and we are on Twitter, and we are on YouTube. We have a number of YouTube programs that talk about the history of the transit and those sorts of particulars. And the map is filling up with locations where you'll be able to view it firsthand or through museum activities. Now, of course, there is an app for that. You can download a free app for timing the transit of Venus, created by Stephen Van Rood. And basically what you do is, you just stand there, and when you see Venus just touching the sun, you click it. And when you see it on the other side, you click it as well. And those numbers are going to get recorded and used in a global measurement of the transit of Venus, the distance thing again. So that's where we get our millions of people involved. We'll at least have millions of apps, people using apps, Hopefully that'll translate into an interesting science result. And of course, if you miss the transit this time, well, you're kind of out of luck. The next one is in 2117. So just add 120 years to your current age, and that's where you'll be. And add that to your grandchildren's age, and that's where they'll be too. So basically, nobody currently alive will probably be alive for that transit either, except maybe our children possibly. Our kids might possibly make it that long. With a lot of medication and things like that. So that basically rounds it out. So if you have any questions, or if you'd just like to chat. Yeah, oh gosh, yeah, or, in the back.
Where will you be on June 5th?
I actually don't know.
Repeat the question.
Oh, I'm sorry. Where am I going to be on June the 5th? I knew that, well, first of all, on that Saturday, I'm going to be in Boulder giving a class on space weather. And then I'm coming back on Sunday. And then Monday, we have our daughter's, Stacia's, graduation. And so then on Tuesday, so I'm not traveling to Hawaii in any of this. And there's no alternate universe where I'm going to Hawaii to be with colleagues. So I'm probably going to be in the Washington area. I don't know. I might even be down here at the Library of Congress, with you guys, with the glasses. That's something that I didn't do last time because I was in Greece. This time, I might just, come to the library here and we can figure out where a good place to view it is. I don't know if the cafeteria would be open at that time. That might give us a good view. We'll figure it out. There's time. Question in the front?
Yeah, is anybody doing using spectrographs to look at the atmosphere of Venus?
No. It turns out that once upon a time, that was an interesting thing to do from the Earth. But now that we have spacecraft that, have gone there, have, cleaner data on the composition of the Venerian atmosphere, we don't need something as crude as the transit to give us that. And also the atmosphere of Venus at our distance is just a very, very thin little breath of whatever around the disk of Venus. I mean, if you think about it. So you really can't really observe the atmosphere very easily from the Earth. I mean, you really have to be close up to do that. Yeah.
In terms of the parallax measurement, is it the time difference depending on the different locations at the onset and the completion, or is it the angle difference that is significant?
It's one is actually related to the other. Here's how we can do this. There's no step down, but if you were to sort of look at me with one eye, if you're looking at me right now from this side of the auditorium, you're seeing me against this screen, lined up with one of these columns in one perspective. Those of you over here are seeing me lined up with the American flag over here. That angular distance that you see me shifting back and forth here in degrees is related to how far apart you guys are sitting in rows and meters. So if you're sitting at the North Pole of the Earth and you're sitting at the South Pole of the Earth looking at Venus, I'm shifting basically up and down because north and south is this way, and so on the face of the sun, the disk of Venus is shifting up and down this way. So that distance that you see Venus shift is measured in degrees, but that's related to the distance in kilometers that I am between the North and the South Pole in my perspective. So it's a matter of basically similar triangles, but you can then work out what the distance is between Venus and the Earth using that angle information and the actual physical distance between the baseline positions. So now where does the timing come in? Well, the thing is that it's easy to find the distance between two lines when you draw them on the sun. It's a little bit harder just looking at the disk of Venus at one moment and the disk at the other, because you have to time your measurements to be identical in time. Otherwise, Venus will be over here or over here. So if you just measure the lines, then you've got the complete information, and you can use multiple measurements of where Venus is in time and draw a line through that very precisely. But that means you have to know pretty accurately to within less than a minute when the transit started and when it ended, okay? Because that gives you a unique angular distance on that chord. You compare that angular distance against some other observer's measurement, and you'll see that they're different because of this parallax shift. The chord up here is a little bit bigger in length than the chord down here, closer to, the curve of the sun. So you basically use that, and it's all related back to a proportion. But you have to measure those times very accurately because that helps you discriminate the distances between those two chords. If you don't do that timing well enough, the chords look like they're essentially the same length, and the process collapses. So that's why timing is very important. And basically all you need from one location is the answer for what was the length of the chord that was measured. You don't need the actual number for the time, because once you get the angular distance, that's all you need. So it's easy to compare one observer's number against somebody else's number because you no longer have to worry about time information. You're now talking strictly about what the length of the chord was, and that's all you need. So it's a much simpler kind of a datum to work with. Very long answer, short question. That's how scientists work sometimes. Yeah.
I have a question about the astronomical unit.
Yeah.
And that's the distance between the Earth and the Sun, right? So.
He had a question about the astronomical unit. Yes.
Yes. Since the Sun and the Earth are not it's not a circular orbit.
Yeah.
I mean, do you have some reference for?
Exactly right. The orbits are slightly elliptical. So the astronomical unit is an established average value that is used to define that orbit. It's not exactly the semi-major axis of that ellipse. It's not the semi-minor axis, but it's a number that you get that you can then convert into one or the other of those two. So it's, you don't have to make multiple measurements of the Earth-Sun distance to get the math to work out correctly. You just need this one number, which is the average. Okay, and you can measure an average very precisely from lots of data. Yeah. Uh-huh.
Could you explain the astronomical underpinning as to why the transit is only visible during the solstice, and also why it flips from winter to summer?
Well, that's why is it only during the solstices, which is basically December and June, and why do we have this flipping? It's all about the timing of Venus in the orbit. Okay, it's a timing issue. It's nothing really more profound than that. You have two nodes defined in the orbit. Okay, those nodes usually line up with the solstices, but not always, because they're rotating, because the orbits are rotating very slowly in time. That's why the particular dates change. Okay, its last transit was on June 6th or June 8th. This time it's on June 5th. Other transits will have different dates, as the orbits change a little bit. It's where this nodal line is, all right? And that's the important thing. And then everything else is about when does Venus get to that nodal point at the same time that Earth is also on that line. And when you work out what those things are, then you have basically two places where that can happen, either in December or in June, okay? And you also get, for instance, the 8-year period is pretty easy to work out because the time between Venus being in the same orientation relative to the Earth and the Sun, that's called the synodic period, and that's about 580 days. If you multiply basically 580 days times 5 and multiply 8 years times 365, you get the same number of days. So that's why 8 Earth years gives you 5 of these synodic points along the orbit, which is this pentagon thing. All right. Now, the rotation of that pentagon is then what determines this 115, 120 year period, and that's more complicated to explain. And I don't really have a good intuitive way of describing that to you. The 8-year period is easy, the 120 year and 105 is harder. Yeah?
Do you know if the National Observatory is doing anything for
The U.S. Naval Observatory. I think Homeland Security has pretty much put the kibosh on anything other than viewing for Congress and the president and families. That, I can't imagine U.S. Naval Observatory being open to the public, and I don't think they are, actually. If anybody here knows more about that.
They used to have an open house.
I know they did.
But is that no longer?
I don't think it is. I think the Homeland Security issue has become just huge because it's the vice president's backyard, Other questions?
Is Air and Space going to have something?
Yeah, I think most places around here will have some kind of a program or viewing. And the amateurs in this area, amateur astronomers in this area are extremely active. They got one more shot to get this right, and it's another 105 years, so they got it really right the last time, but, this time it's the grand deploy. Plus, I think daisies will be very popular. That's a subtle comment about Bill Harkness's comment about daisies bluing in 2004 for the next transit. Yeah.
My question is not about Venus, but I'm from Indonesia.
Mm-hmm.
When I was in Indonesia, when I looked at the moon,
Mm-hmm.
I thought, how did they come up with the moon having a face?
Yeah.
Because in Indonesia it looks different.
Uh-huh.
And when I came here, I look at the moon when it's full moon, and I thought, right, I see the eyes, I see the nose, I see the mouth.
Yeah.
And in Indonesia, I went back to Indonesia, and it's not there. And I don't know whether it's my mind or what. It's different.
Now, correct me if I'm wrong. Indonesia is, much of Indonesia, is that not south of the
Tropical.
equator?
It's
Or-
right.
All right, so you have this problem with the moon maybe being upside down.
Yeah, it's really funny. In
Yeah.
Indonesia, it's an
Yeah.
old woman carrying wood.
Okay, all right, all right.
Nothing with the face at all. And
Yeah, I know. Yeah, it's
and I thought, is it just me or what?
Yeah.
Nobody ever said anything.
yeah. I've looked at the moon countless times as an astronomer, and I don't get it either. And the only thing I can think of is it must be medication or drugs. Or the quality of the water. It's got to be something like that. 'Cause I'm a fairly imaginative person, but I look at the moon and I basically see, yeah. Mhm.
For those of us traveling, what parts of the world will this be visible?
Gosh, it's going to be visible anywhere. Anywhere from Japan, Hawaii, Western United States, Eastern United States, Europe. I think there's only a sliver between Eastern Europe maybe and India or whatever, where they don't get to see much of it. There are many of these maps online you can go to, but we're pretty good. Actually, Pacific, the Atlantic Ocean is a bad area because the transit will basically happen after local sunset, so you won't see it. You just have to go 2 more time zones to the east of us, and the transit happens after sunset. And that continues on, for, 8, 9, 10 hours. So yeah, I mean, we get it this time. Last time, Europe and Asia and everybody else got to see a really good transit.
2004 we couldn't see it here.
Let me see. We saw only, I think, about the last hour of it or something, because we were on sort of the other edge. And then you went, to the middle United States, and they wouldn't see it because it happened, after sunset or whatever it was. So it's a little bit complicated, but we've worked that out. You can just go online and see these maps. And, if you're in Washington, you're going to be fine. If you're on the West Coast, you'll be fine too. If you're in Europe, you won't be quite so fine. Much better food though. Yep.
There is an annular eclipse of the sun on May 20th. It's kind of a warm up back. Big deal has to have a warm up back.
That's right. That's exactly right. Yep. Uh-huh.
You said you were kindly bringing glasses. How will we know when they arrive?
I think I'm going to be getting the shipment this Friday, so I would think by sometime earlier next week I'll be able to bring the glasses in here.
We'll have them in the Science and Business
Yeah.
Reading Room, so you can call the Science Reference Desk probably that would be the best to make sure they're there rather than just stopping in next week.
Yeah.
And we have bookmarks out front that have our phone number. They can contact us directly.
All right. How are we doing on time? 12? Okay. All right. One more minute to go.
Just a follow-up.
Yeah,
Another
okay.
question. Does it matter the longitude? For example, if you're in the our time zone, is there a point as to how far south or north it can be, and that would impact if you're in a different place?
Yeah, if you're, for instance, if you are located on the east coast of the United States and you go down in longitude too far, you will be in that zone where you won't be able to see it. So the zone probably goes into Brazil. By the time you get that far south, you'll also be in the embargoed zone. But if you're on, for instance, the west coast of the United States, you have to go, quite far down through South America's latitude in order to get into that. So, it's different. It depends on where you are. I mean, in fact, at the longitude of Hawaii, you can view the transit all the way up in Fairbanks, and I think all the way down practically to Antarctica. It's that huge. Okay, well, thank you so much for coming. As soon as I decide whether I'll be here on the 12th, I hope to see you, if we can sort of figure out how to coordinate that, on 6 o'clock, June 5th, Tuesday. And you'll have your glasses ready to go. Thank you.
This has been a presentation of the Library of Congress. Visit us at loc.gov.